So we have di by dA equals 2j over pi, where j is given by this. We're just doing half of the integral over all x to get, this is just the same as the integral from 0 to infinity, which then gives us this when we differentiate. Right, so we need to evaluate this. And we can do that by considering the real parts of e to the iau in here. So we've got this is now plus iau. And then completing the square, okay, so to complete the square, we'll take out a factor of t, and then to get that we need, this is outside the brackets, we need another minus here, and then it's going to be minus ia over 2, so that when we square this, we'll get a minus ia times u, we'll get the u squared, and then sorry, I forgot a factor of t. So we've got a factor of t, which I've taken out. So to avoid that factor of t, we need this t here. Okay, since we're multiplying this by t, when we expand this out to get rid of that factor of t, we need this t here. And then I've got one extra term inside here, which I didn't have before. So if I expand this, I will get, because of the minus sign, I'll get a minus this thing squared, a over 2c squared, 2t squared, and then I've got a minus t multiplying that. So minus minus makes plus, which means I need to compensate by adding a minus, and it's going to be a squared over 4t squared times t, so it's just a squared over 4t. du. Okay. So this I can take outside. So I've got e to the minus a squared over 4t over 2. And then that just leaves me with this integral here. And then I can do, well, I can do a change of variable. To keep this short, it's possible to show carefully that this is still with the u minus I times a real constant. It's possible to show that this is gives the same answer as if you didn't have this here, actually using complex variables. We might skip that leave that till the end. So making a change of variable, so I'll just make minus over root t. Sorry, it should be times root t. Then I need to divide by root t here. Then this is just going to be the famous result root pi. So I ended up with this equaling e to the minus a squared over 4t over the answer to this integral is root pi, and it's 2 root t on the bottom. Okay, so now we go back and use this result. So if I integrate both sides of this equation, I will get, the quick way of doing this is to, I'm integrating, I'm integrating with respect to a. So if I'm integrating di by dA with respect to a, I just get I. So I get I, and then I can choose my limits of integration to be values of I. So I choose them for different values of a. So I choose it to be I at 0 t, and then actually the thing I'm trying to find is I a at t. So I'm integrating this with respect to a. The dA's cancel and I get di. And on the right hand side, okay, I've got to integrate this with respect to a. So I've got 2 over pi. I've got root pi here, so that gives me this. I've got a t, and I've got this 2 here, which cancels this 2 here. So I then have the integral from a equals 0 to a, and I have to relabel my a here, so I call it a dashed or something. So it's minus a or a dash squared, okay. And that's all I have, okay. And d a dashed. So making a change of variable, I'll let b equal a dashed b squared equal a dash squared over 4t. Which means, okay, I'll just square root things, it's simpler. Which means that dA dashed is equal to 2 root t dv. So making that change of variable, the root t cancels this root t, and I get 2 over root pi, 0. V is equal to this over this, so I've got a over 2 root t on the top, and I've just got e to the minus v squared dv. Now this is actually a well-known integral, which can be written, we've got it exactly right now. This can be written in terms of what's called the error function. So this is actually simply the error function of this thing here. So in case you haven't met these before, the error function is actually defined by this integral. So it's 2 over root pi, the integral of Gaussian from 0 to x. It's actually a very useful function, both in probability theory and in heat conduction. So this integral here, which I then need to actually say what this thing is. So we've got I of at, and then when a equals 0, what is I? Well, when you've got sine 0, so that's just 0. So this is actually just 0 in the end. And we have that IAT is equal to earth a over 2 root t. And the final thing we're looking for is actually f of t, which is 1 minus I. And actually, there's a special function called the complementary error function earth c, which is precisely 1 minus earth. So we can write this in the most compact way as earth c of a over 2 root t.